Today we'll be talking about Lagrangian and duality. One of the prime reasons behind this discussion is that when we were discussing about SVMs and we were looking at the primal and the dual objectives, at one point of time I made the statement that the minimization of the primal objective is the same as the maximization of the dual objective. So this wasn't really clear, where does this minimization in the primal suddenly give you maximization in the dual. In today's lecture we'll understand some of the maths behind introduction of Lagrangians and duality, and I should make this clear upfront that this is again going to be a pretty optional video, given that the mathematics involved would be fairly non-trivial at different points of time. So before we get into what we did discuss in the SVM, etc., I'll start off by first stating an inequality. Then we'll go on to prove this inequality, and then we go on and show that how the Lagrangian was even formulated. So I'm going to call this inequality as the minimax inequality, which states that for a function q which consists of two variables x and y, for all values of x and y, this inequality holds. The inequality says that if you do first a min over one variable and then a max over the other variable, or maximize over the other variable, that would be lesser than or equal to if you maximize over one variable and then you minimize over the resultant function. Now, in order to prove this, for all x and y, we'll first prove something which is simpler, which just looks at the inner terms, that the minimization over one of the variables will be lesser than or equal to the maximization over the other variable. And we'll take a specific example to try and understand this formulation better. So let's choose a really simple function q of xy equal to xy, and first let us try to find out the maximum of this function, or find out how we can maximize this function over the variable y, right? So if you maximize this function over the variable y, this would become a function of the variable x only. It will not remain a function of y any longer. So let's just take a few values of this function qxy in this tabular format. So I'm going to talk only about a discrete set of values for now, but the principles will be general. So I have the variable y over here, 1, 2, 3, 4, and x over here, which goes from 1 to 3, 4. And in this table, in the tabulated format, we have the values of x and y, right? The first thing, okay, so we said that we want to find out first the we want to maximize this function over the argument y, right? So essentially what that means is you look at a value of x, right? You look at, let's say, x equal to 1. You see the y which maximizes xy. That y turns out to be y equal to 4, and correspondingly the function value is 4. You look at x equal to 2 and you find out the y which maximizes this function qxy. Again, you look at x equal to 3 and you find out the y which maximizes qxy. Similarly, you look at x equal to 4 and you look at the y which maximizes qxy. So essentially what you're trying to do is to look into each row in this matrix and figure out the y's for which we'll have the maximum entry on a per row basis. Given the structure of this particular function, it turns out to be that the last row or the highest y would be maximizing this function. So if you indeed keep y equal to 4, then the function will become qxy would now be transformed to a function only of x, which would be 4x. And as you would have already seen, 4x will be greater than or equal to 3x, will be greater than 2x, greater than 1x. So for all values of x now, you have obtained the maximum, you have chosen the y value correspondingly, and you've found out the y which will maximize this function. And now we can do something similar. Now we can find out for each value of y we can find out x that minimizes qxy. So first we're trying to find out a y which maximizes qxy, and then we're trying to find out trying to find out x for each value of y that will minimize qxy. So you look into the different columns. You first look at the first column, y equal to 1. You look at the x which will minimize this qxy, and since y is already known, so it's only a function of x, and that will be 1, x equal to 1. And similarly for all the different values of y, you can see that x equal to 1 in this case, or this particular example, will lead to minimization of qxy, right? So we have, if you just look at what we have done, we have indeed shown that for all x and y pairs, or for all xy, if you minimize this function qxy of two variables over one of the variables, that would be lesser than or equal to if you maximize the function over the other variable, right? So if you look at all the different functional values that you've obtained, 1, 2, 3, 4, when you were trying to minimize with respect to x, or if you look at the maximum values, or if you look at the functional values when you were trying to maximize the function qxy with respect to y, you'll see that for each of them values are lesser than equal to the values that you obtained in this function, in the maximization, in the right hand side function, right? And the equality occurs at this particular point when x equal to 1 and y equal to 4. So we've been able to, through a help of a trivial example, show this identity, and now we'll be making use of this identity to go ahead and prove the minimax inequality. Now let's now try to find out, if you do min over x of the original function qxy, you'll get a function of y, and then you maximize that function over y and you'll get some values, right? So if you found out the min over x, you'll get y equal to 1, 2, 3, 4, right? And then if you maximize this thing over y, right, you find out a y which maximizes these values, then you'll choose y equal to 4. So min of qxy over x gives you this range of values 1, 2, 3, 4, or basically corresponding to y equal to 1 you get the functional evaluation as 1, for y equal to 2 you get functional evaluation as 2, so on and so forth. Corresponding to y equal to 4, you are able to maximize the new function obtained, and that gives you a value of 4. Similarly, we can first find out the max. You can maximize the function qxy over y, which was giving you these 4 functional values, right? Corresponding to x equal to 1 you got 4, corresponding to x equal to 2 you got 8, corresponding to x equal to 3 you got 12, and corresponding to x equal to 4 you got 16. And now you're trying to minimize this new function of x over x, which means that you'll end up choosing x equal to 1 corresponding to a functional value of 4, right? So when we were finding out the max min, we found the value of 4, and if we did min max, we found the value of 4. And for this trivial example, we can see that the max min is less than equal to min max. So the min max was correspondingly found here, and the max min was found using the yellow color. And we can see that for all values, we'll basically be able to show this particular identity, that there will be a lesser than equal to equation or relationship between them. So this can also follow even without having to work through this example. If we just go back from the identity that we saw, right? So we've been able to show that the min of this function, so if you minimized over x and you get a new function of y that is always less than equal to this particular function, right? Now if all of the values here are lesser than all of the values here, then the max of the values here will always be lesser than equal to the min of all of the values here, less than equal to, right? So that's another way to look at the same thing, and that's exactly what the example also ended up showing. The max of this particular function was 4 and the min of this particular function, which is evaluations are shown in purple, was also 4. So thus we have seen a trivial way to show the minimax inequality, that max min is less than equal to min max. Now we'll be making use of this result and understanding the relationship between the primal and the dual. But before we do that, we'll revisit the Lagrangian multipliers and understand them in now even more depth as to why there's a particular form of Lagrangian multipliers that we study. So our problem is of the following form. We're trying to minimize a function of x over x subject to inequality constraints, m inequality constraints gi of x, which are of the form less than equal to 0. And the idea is to convert this constraint problem. So if we were to only minimize fx, it is an unconstrained problem, but we have some constraints. So we want to convert this constraint problem to an unconstrained problem, because we know that solving unconstrained problems is easier. So one way in which we can convert this constraint problem to an unconstrained problem is to create this new function of x, which is fx plus summation over all the inequalities of this step function, this infinite step function applied over gi of x. So you've plugged in all of these values inside this infinite step function, and now this is a single line equation. So now this is not subject to anything per se, but we need to define what this infinite step function is. This infinite step function has to satisfy these constraints, right? Because that's the way in which we want this problem to be solved. We want that the constraints should be satisfied. So this function of, if this function for any argument z is 0 if z is less than equal to 0, which means that if the constraints are satisfied, then there is no cost to be added, no penalty to be added. But if the constraint is not satisfied, then you add an infinite penalty, which basically means that there is no way in which the the constraint is violated, because that is the form that you want, that is the problem that you want to solve. But unfortunately, this formulation is equally hard to solve. Like, there is no trivial way in which you can solve this. And what you now want to do is to write this or replace this part of the unconstrained problem with something which is easier to solve, and we can use some bounds on this on jx. So that is the main idea which we'll look now. So we'll introduce the Lagrangian multipliers, and the idea is we want to approximate jx, because getting jx correctly means using the infinite step function, which is not going to be trivial to solve now. So we create this function, Lagrangian function, which is now a function of the original variables x and a function of the newly added variables of Lagrangian multipliers lambda, which is fx plus summation I equal to 1 to n lambda I gix. Now if you look at, or if we compare the infinite step function with this function, you'll see that they're fairly similar in form, but there is a main difference that now you're multiplying a non-negative quantity instead of multiplying an infinite quantity in case the constraint is violated. So natural question at this point of time is that what is the relationship between the Lagrangian function of, which is a function of x and lambda, and j of x. And we already know that lambda I all lambda i's are greater than or equal to 0. So I would request you to pause the video for a minute and think about this particular question. Assuming you paused the video and thought about this, so the answer is that when lambda is greater than or equal to 0, lambda vector, or each of the lambda i's are greater than or equal to 0, then the Lagrangian is a lower bound of g of x, because the maximum that you can get in this function lx lambda is going to be g of x, right? Because you can then you can take the lambda values to be equal to infinite, and that's how you will be able to get to g of x. So we'll be making use of this particular identity, that g of x is maximization of this function lx lambda over the lambda variables, but there is a small constraint here that the lambda is greater than or equal to 0 here. So we have, rewriting this thing again, we have jx is the maximization of the Lagrangian function over the variable lambda, but with the constraint that lambda is greater than or equal to 0. But if you remember, our original formulation was minimizing g of x. If we go back, the way we introduced jx was, so the original problem was minimizing fx subject to these constraints. We wrote a new function which we were still trying to minimize, and it is an unconstrained problem. So the original formulation is, or the original problem is to minimize g of x, and we have just now written that g of x is equal to, in this particular format we have written, it's a maximization over the Lagrangian function containing the variables x and lambda, where lambda is greater than or equal to 0. Thus the original problem of minimizing g of x can be equivalently written as, first you find out g of x, which is the maximization of the Lagrangian function of x and lambda, and then you minimize that over x, right? So again, g of x was minimized over x, and the Lagrangian function to obtain g of x is maximized over lambda, where lambda greater than or equal to 0. But just a few minutes back we proved the minimax, or we looked at the minimax inequality. So the minimax inequality, if we write it down here, we can write that min max over the Lagrangian function is greater than or equal to the max min over the Lagrangian function, right? So in the max min formulation, you first do the minimization over x, and then what you get is a function only of lambda, and then you can maximize it over lambda. So that's essentially what I'm going to do now, that I'll write the dual objective function. So the dual objective was written in this particular format. We wrote the dual is going to be now, so the primal was a function of the original variables x, the dual will be a function of the new variables lambda, and it will not be a function of the original variables x. So if we look at this particular quantity, so either if you look at, in this case, the maximization over L or the minimization of this L, what you'll get is you'll get a function only in lambda. Sorry, you'll get a function in lambda in this particular case, because you are firstly finding out you're looking at the values of x, which will minimize L of x lambda. So we write the dual objective as a function of lambda, which is d of lambda is the minimization over x of L of the Lagrangian function, which is a function of x and lambda. Now what this gives us is that if the original primal was minimization over x of the function fx subject to a set of constraints, or the primal objective was g of x, which is greater than or equal to maximization over lambda of d of lambda, right? So G of x is our primal objective. Maximization over lambda of d of lambda is our dual that we're trying to maximize now, right? So what we're basically getting is that the minimization of the primal is greater than equal to the maximization of the dual. But the important thing to note is that again is that the primal is in terms of x, original variables x. The dual is in terms of the new introduced variables of the Lagrangian multipliers. And so we've basically written, what we've shown is that is known as the weak duality concept, that the primal objective is greater than equal to the dual objective, but for specific cases of problems like the SVM like formulations, the primal objective is the same as the dual objective. So this inequality greater than equal to is actually unequal. The primal objective is the same as the dual objective, and this particular property is known as the strong duality. So this is how we can show that in the case of SVMs, the minimization of the primal in terms of the variables, primal variables w and b, is the same as the maximization of the dual, where the dual is in terms of the variables alpha, and you try to maximize that over alpha. So both of the objectives are the same. It's just the primal dual way of looking at things. And this does not necessarily hold for all types of problems. The relationship between the primal and the dual, there is generally a gap between the primal and the dual, that is known as the duality gap. But for problems like SVM, that gap is 0. So with this, we'll end this particular discussion. Again, do not worry if you do not get all of this. A lot of this material is referenced from the excellent textbook called Mathematics for Machine Learning, which you can also refer to understand this lecture even more. Thank you.